This Zoom session is being brought to you by the Fractal Snowflake Curve. All right, now we begin. So we're going on about systems of inequalities. Okay. The graph of an inequality, such as minus 3x plus 7y is greater than 21. The greater than sign makes it an inequality. It's the set of points on the Cartesian plane fitting the given inequality. Spit check. Okay, we're all here. Pretty much. All right. And in general, the graph of a linear inequality is a half plane. So for example, minus 3x plus 7y is greater than 21. Now, because it's a strict inequality and not a greater than or equal sign, the boundary line is excluded. So I denote that as a dot, 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 rather than as a solid line. And if you check, if you set x equal to 0, then 7y is greater than 21, which makes y greater than 3. So everything above this value, 3. If you set y equal to 0 here on the x-axis, then minus 3x is greater than 21, so x is less than negative 7. So here's negative 7 and everything to the left of that. This dotted line is the graph of the line through minus 3x plus 7y equals 21. And we color in half the plane, namely this half of the plane, which these two arrows are pointing into. So it's going to be this half plane. Minus 2x minus 3y is less than or equal to 9. Since it's a less than or equal sign, the boundary line is included, and so we draw it as a solid line. As before, we'll find the intercepts of the boundary line. When x equals 0 here on the y-axis, then we get minus 3y is less than or equal to 9, so y is greater than or equal to negative 3. So here's negative 3, and I point to greater than or equal to it. So this half of the plane. When y is 0 here on the x-axis, then 2x is less than or equal to 9, so x is less than or equal to 9 halves. Here's 9 halves and pointing to the left of it. So we'll have, and this is the graph of the boundary line, which I draw solid, and this is the half of the plane that I color in. This is nonlinear. So x squared plus y squared is greater than 100. The boundary line is a circle, we included, and it's a circle of radius square root of 100, radius 10. And so you have this circle, we bound and we color in everything outside the line, outside the circle. All right. Now, if you have more than one inequality, a system of inequalities, then the graph of that system is where each of these inequality graphs intersect. If you have a system of linear inequalities like this, then you'll wind up drawing an intersection of half planes. So for example, x plus y less than or equal to 4, here's the boundary line, x plus y equals 4, and it turns out to be everything below and to the left of that line. Y greater than or equal to x, here's the line y equals x, and we color in everything above the line. We want to know where above this half plane here meets below this half plane here. That'll be a quarter of the plane like this. Now, I have a strong request. Often I see someone told to graph this system, and what they do is they color in this and this and this, and I marked it wrong. If a system is where the half planes intersect, where they overlap. So in this case, it would be a quarter of the plane. Here's a system of inequalities. Y less than or equal to 9 minus x squared. Here's the graph of y equals 9 minus x squared, and we color in below it for y less than or equal to 9 minus x squared. X greater than or equal to 0. Here's the line x equals 0, and everything to the right of it is x greater than or equal to 0. Here's a line y equals 0, and I'm coloring it, and everything above it is the half plane y greater than or equal to 0. So you find out where these three parts of the plane intersect. And they intersect in just this part, not anything else. Or x greater than or equal to 0. Well, here's a line x equals 0, and we want to color into the right of it. Y greater than or equal to 0. Here's a line y equals 0, and we color in everything above that. X less than or equal to 5. Here's the line x equals 5, and I were to color into the left of that. And oh yes, you'll notice I'll put these little arrows in indicating which half of the plane you're supposed to be coloring in. Here, 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 and here, here, here. Okay, x plus y less than or equal to 7. Here's the line x plus y equals 7, and x plus y less than or equal to 7 is everything below and to the left of that. So we want to find which part of the plane all these little arrows I drew in point inwards to. It's, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 parts of the plane. The 10, I'm sorry. Which part do we color in? Well, this has these two pointing in, but not this. So no. These two point away, this points away, and so on. This four-sided figure has all the lines, little arrows pointing inwards to it. So it's going to be this part of the plane coloring. Okay, now the purpose of this, well, this is one of those things of the book, this is one of those topics where you can either ignore completely or just sort of briefly glance at, which is what this does, or you can write a whole thick book about it. It's related to something called linear programming. And the idea is you'd be given a set of constraints such as this. X and Y would be like productions of, well, let's say shoes and sneakers. You have to make at least no shoes and at least no sneakers, and at most five shipments of shoes. And the total number of shipments has to be less than or equal to 7. This region in here is called the feasible set. The set of possible values of X and Y that are allowed within these constraints. And the question is, what set of what production schedule, what production program gives you the greatest profit? Because presumably the shoes give you a certain profit, the sneakers give you a certain profit. Which of these possible linear programs maximizes profit? It turns out that profit, if the objective function, when being maximized, is a linear function, then, and the objectives are all linear, then the maximum and the minimum occurs at one of the corner points. So in linear programming, you start with an objective function and these constraints. You graph the constraints, find out the corners of the feasible set, and evaluate the evaluate the objective function at those corners, and the maximum of that is a maximum profit. And like I say, this is something that they used to cover in great detail, but it's sort of gotten more perfunctory over the years and so on. Well, enough of that. Oh, and by the way, nowadays the theory of linear programming has gone way beyond the system I just described. It involves massive computers and solving problems of tens of thousands of variables and so on and so forth. Never mind that. Okay, we have concluded chapter 5. So let's stop recording.